Hi, this lesson is about sketching a curve by using information from the first and second derivative. So with the first derivative, the sign of the derivative is important. If f prime is positive on an interval, then your function is increasing on that interval. If f prime is negative on an interval, then the function is decreasing on that interval. And if f prime equals 0 and that has a solution, those are critical points. And critical points could be maximum or minimum points on a graph, but they also could be inflection points, and we'll talk about that later. So we have something called the first derivative test. And the first derivative test says that if c is a critical point on a function, and if your derivative changes from positive to negative before and after c, then f has a local maximum at c. And then similarly, if you have a critical point where the derivative sign changes from negative to positive, then you have a minimum at c. If there's no change in sign, then you don't have a maximum or minimum. So to illustrate that, here's a picture. This looks like a polynomial. So if I have a critical point, which I'll call c sub 1, and another critical point, which I'll call c sub 2, when I'm to the left of c sub 1, my first derivative is positive. That's because the slope of the tangent line on that side is going upward from left to right. But then after c sub 1, the slope is negative. So that means that at c sub 1, I have a maximum. So there's a change in sign in terms of the derivative before and after it. Similarly, before c sub 2, the slope is negative, but after c sub 2, the slope is positive. And so when the slope changes sign from negative to positive, you have a minimum. So that's basically what the first derivative test is telling you, that if you check the signs of your derivative and there's a change in sign before or after the critical point, it could be either a max or a min. So here's an example, given that f of x equals x to the fourth minus x squared, we want to determine intervals where f of x is increasing or decreasing, and then identify points of extrema. Remember, extrema is just a general term to say maximum or minimum points. And when we're talking about intervals, we're talking about intervals of x, and those intervals should always be open intervals, never closed. All right, so we have f of x equals x to the fourth minus 4x squared. Take the derivative, that's power rule. 4x cubed minus 8x, we set that equal to 0. This is factorable, so we get 4x times x squared minus 2. Take each factor, set it equal to 0, and you get x is equal to 0 and x is equal to plus or minus root 2. So those three numbers, 0, negative root 2, and positive root 2, are your critical points. And we put that on a number line to keep us organized. So you see that here. Put them in order, negative root 2 first, then 0, and then root 2. Okay, so notice that there are pluses and minus signs above that number line, and that's just to keep us organized. It's just a quick way of keeping track of things. So you're going to pick a test point to the left of negative root 2 and plug it into your first derivative. And so the easiest place to determine the sign of that result is to plug it into the factors here, 4x times x squared minus 2. So pick something less than negative root 2. So negative root 2 is about negative 1.2. So if I pick negative 2, that's a safe number to pick that's to the left of negative root 2. But you can pick anything you want. You can pick negative 3, negative 10, negative 1,000 if you want to, but keep the numbers reasonable so that they're easy to compute. So this is now what we consider to be the first derivative test, where you're plugging in numbers and checking the sign. So I'm going to plug in -2. So 4 times -2, that's a negative result. And then -2 squared minus 2, that's positive. A negative and a positive gives you a negative result, which means that your function is decreasing. Then I pick a number between -√2 and 0. -1 is a good choice. Again, plug it into your first derivative. That'll give you a negative and a negative. Two negatives make a positive. Positive means that the function is increasing. Then pick a number between 0 and +√2, like 1. Plug that into your first derivative. So you get 4 times 1 is positive, 1 squared minus 2 is negative, a positive and a negative is negative, which means the function is decreasing. And then pick something greater than √2, like 2. Plug that in. You get 2 positive results. So 2 positives make a positive. So it's increasing, right? So a summary of what we found in your first derivative is that it is increasing from -√2 to 0, and again from √2 to infinity, and it's decreasing from -∞ to -√2, and again from 0 to √2. Again, put your intervals of increasing and decreasing as open intervals, so use parentheses, not brackets. Okay, but the first derivative test told us that we have maximums and minimums here. Let's start with -√2. -√2 is a minimum because before it's negative, meaning it's decreasing, and after -√2, it's positive, meaning it's increasing. So that gives us a minimum point at -√2, f of -√2. So you find the actual point by plugging into the original function. Remember, this is your original function, x to the 4th minus 4x squared. When you plug in -√2 into that, you get -4 as a result. So -√2, -4 is your minimum point. So let's move on. At 0, I have a maximum because the sign changes from positive to negative. In other words, the graph is increasing then decreasing, so that's a maximum. And when x is 0, f of 0 is also 0. So 0, 0 is a max point. Okay, then we have another extreme value at √2. At √2, I have a minimum as well, because before √2, it's negative, decreasing, and after √2, it's positive, increasing. So we have a minimum at √2, f of √2, and again, if you plug in f of √2 into the original function, you get -4 as a result. So √2, -4 is a minimum. All right, so we've answered the questions in the problem. Let's move on to information about the second derivative, which is concavity and inflection points. So first let me explain what concavity is. So a graph is concave up if the graph is facing upward. So an example of a concave up function is your parabola y equals x squared, which I've plotted here for you. So that's a very traditional concave up shape, like a U shape facing upward, but it could be more subtle, like these other two on the right. So it could be facing upward like this, or more subtle concave up. This one here is increasing but concave up, or it could be something like this third option. This one's also concave up, but this graph is actually decreasing. So the opposite is true with concave down. With concave down, the graph opens downward or faces downward. So an example would be something like -4x squared. That's also a parabola. It's a little skinnier than x squared would be. So that's what you see here. This is -4x squared. That's a traditional concave down shape. But again, it could be more subtle, like this first example here. This is concave down as well, this is increasing and concave down, or like the last option here, this one is decreasing, but also still considered concave down. All right, so this is referring to something I haven't drawn yet, so let me draw a picture to explain inflection point to you. So a point on F is considered to be an inflection point if that point exists on the curve and there's a change in concavity from concave up to concave down, or from concave down to concave up. So we find inflection points by solving f prime double prime of x equal to 0. So when f double prime is positive, it is concave up. When f double prime is negative, it is concave down. So when you see a change in sign from concave up to concave down, that means that you have an inflection point where that transition happens. So let's look at an example of that. It'll make more sense once you see an example. So we want to identify the intervals of concavity and inflection points for f of x equal to x cubed minus 9x squared plus 1. So first find the first derivative. So we have f prime is 3x squared minus 18x. But with concavity and inflection points, we need the second derivative. So that's what you see right here. That's f double prime is 6x minus 18. That's the equation that you set equal to 0. And when you do, you solve it, you get x is equal to 3. That means that 3 is a potential inflection point, but we have to test it. So this is what we consider to be the second derivative test, where we're checking the sign to the left and right of this potential inflection point, and if there's a change in sign, then it's an inflection point. So you take a number less than 3, and again, choose anything you want. There's no restrictions on domain. This is a polynomial function. You plug it into your second derivative. So suppose I pick 2. Plug that in, I get a negative result. And a negative result means that the function is concave down from negative infinity to 3. If you pick another test point, but to the right of 3, such as 4, and plug it into your second derivative, well, there you get a positive result. Positive means it is concave up. So because there's a change in sign from negative to positive, in other words, from concave down to concave up, then you can safely say that there's an inflection point at 3, f of 3, and when you plug in 3 back into your original equation, you get that when x is 3, f of x is negative 53. So you have an inflection point at 3, negative 53. Okay, but I also know that the graph is concave down from negative infinity to 3 and concave up from 3 to infinity. All right, so let's move on and actually sketch a graph. But in addition to using the first and second derivative, we should also consider the domain to help us graph a function. Intercepts, especially y-intercepts, are easy to find, so we're going to look for that. And asymptotes. Some graphs have asymptotes, some don't. But if they have asymptotes, that's something you want to consider because it gives you a more precise graph. All right, so our first example is to sketch the curve of y equals x over x minus 2. This is a rational function. Rational functions are functions, they look like fractions where you have at least one variable in the denominator, so this one certainly qualifies. With rational functions, you often have a restriction on the domain, but not always. And the way you know if there's a restriction on the domain is if you can solve the denominator for 0 and get a real number result, then that answer, which in this case is 2, is not a solution. It is the value that needs to be excluded from the domain. So your answer to domain is that the domain is all real numbers except 2. So in interval notation, that's negative infinity to 2, union from 2 to infinity, and my intervals are with indicated with parentheses because instead of brackets, because you don't want to include the 2. Asymptotes. Rational functions often have asymptotes. So whatever value you got as your restriction to the domain is often going to be a vertical asymptote. And you can test that by actually taking the limit, that's what I did here, taking the limit as x approaches 2 from the left of your function and the limit as x approaches 2 from the right of your function. Remember, with limits, when you can't just do direct substitution, you can use values that are close to 2. So for example, on the left side, you can let x equal 1.9999. And if you plug that into a calculator, that might help you see it more easily. You'll get a negative number that's very negative. In other words, it's going towards negative infinity. And the closer you get to 2 on the left, you'll see that that negative number becomes closer and closer to negative infinity. And then you can do a test point here on the right. So let's say 2.0001. That's close to 2, but to the right of 2. And if you plug that in, you'll find that your function is approaching infinity. So again, you can play with different numbers that are getting closer and closer to 2 on the left and the right to help you see that pattern, and eventually you'll be able to conceptually think that through. So that means that x equal to 2 is a vertical asymptote. We indicate that with a dotted line on the graph. So for the purposes of just keeping ourselves organized, anything that I put in a green box will be something that I want to keep track of so that when I graph my function, I actually show that information on the graph. All right, so horizontal asymptotes. Horizontal asymptotes are found by taking the limit as x approaches infinity. And so when I take the limit as x approaches infinity, remember the technique is to multiply the numerator and the denominator by the reciprocal of the variable term with the highest exponent in the denominator, which in this case is x. So you multiply top and bottom by 1 over x. Remember, that's the same as multiplying by 1. So you're not changing the integrity of the original problem, but you're manipulating to help us think this through. All right, so when you distribute the 1 over x, you get the limit as x approaches infinity of 1 over 1 minus 2 over x. And as x approaches infinity, 2 over x becomes a very small number. In other words, it goes to 0. So you're left with 1 over 1, which is just 1. When you get a finite answer, when you're taking the limit as x approaches plus or minus infinity, that finite answer, which is 1, becomes your horizontal asymptote. So y equal to 1 is the horizontal asymptote. You would get the same result if you took the limit as x approaches negative infinity, so we don't need to do the same work twice. All right, so now we're going to use our derivatives. We need to use quotient rule on the original function. Remember, the original function is x over x minus 2. So here's the work for quotient rule here on the right. Your f is the numerator x, f prime is 1. Your g is the denominator x minus 2, g prime is also 1. So when you plug that into your quotient rule, you'll get y prime is x minus 2 times 1 minus x times 1 over x minus 2 squared. Simplify the numerator, it leaves us with the derivative of negative 2 over x minus 2 squared. Remember, you take the derivative and set it equal to 0, but it is impossible for this to equal 0. So that's why I wrote it's not equal to 0, because the only way a rational equation can equal 0 is if the numerator equals 0 and if that solution is in the domain. Well, it is impossible for negative 2 to ever equal 0. So therefore, what that means is that there are no extrema, no maxes and mins. Okay, but that's okay because I can still I indicate that here. So I can still check for the sign of my derivative by plugging in test points to the left and right of 2. Now, why am I putting 2 on the number line here? And that's because 2 is a restriction on the domain. So remember, we talked about that right at the very beginning. 2 is not defined in your original function. Remember, here's the original function. If x was equal to 2, it would be undefined. So you have to check what is the behavior of the function to the left and right of 2. And you check that behavior by plugging into y prime. All right, so I pick a number less than 2, let's say like 1. If you plug that into y prime, you get a negative result, which means that the graph is decreasing to the left of 2. If I pick something greater than 2, like 3, and plug it into y prime, you still get a negative result, which means it's decreasing to the right of 2, or from 2 to infinity. So your graph is decreasing from negative infinity to 2, and then again from 2 to infinity. But remember, at 2, we have an asymptote. Okay, so all this is going to help us to graph it, but second derivative will help us even more. So remember, this is the first derivative. I rewrote it in a different way just to avoid using quotient rule again. I brought the denominator up to the numerator and wrote it as negative 2 times x minus 2 to the negative 2. This now allows me to use chain rule. Chain rule is quicker than quotient rule, although you can use quotient rule if you want to. So when I use chain rule, it's power rule on the outside. Negative 2 times negative 2 gives me 4. And then subtract 1 from the exponent, so that is negative 3. And then the derivative of the inside is 1. I didn't write it, but so that's actually showing you that I'm using chain rule. And then if I rewrite that in a different way, I get 4 over x minus 2 to the third power. So for the same reason I explained above, that rational equation can never equal 0. It has no solution, and that means there is not going to be an inflection point. So again, that doesn't mean that I can't test for concavity. And when I test for concavity, I still need to keep track of what's happening to the left and right of 2, because 2 is not in the domain. So pick something less than 2. Plug it in here. If you pick something like 1 or 0 or negative 1, you will get a negative result. Negative result means it is concave down. If I pick something greater than 2 and plug it into your second derivative, like 3, you'll get a positive result. Positive means concave up. So in summary, it is concave down from negative infinity to 2 and concave up from 2 to infinity. So if you recall, we didn't find any maxes or mins. We didn't find any inflection points. So we really have no points to plot. So we should try to find something. So an easy one is to find an intercept. So when x equals 0, if you plug it in here, your y is also 0. So I have an x and y intercept at the origin at 0, 0. So I'll plot that. All right, so here's the graph of y equals x over x minus 2. So I plotted the point 0, 0. That's what you see here. That's the 0, 0. I know that the graph is always decreasing. We found that with the first derivative. So both of these blue curves are always decreasing. The green dotted lines are my asymptotes. Remember, I had one at x equal to 2, which is here, and another one at y equal to 1, which is here. And then here's our concavity. It is concave down from negative infinity to 2. So that's, again, this part of the graph right here. And it is concave up from 2 to infinity. So that's part of the graph that you see on the right. So there's your picture. It's fairly accurate. You don't really need to find any other points than the one we already plotted. All right, so here's another one. This is a polynomial. So we want to sketch the graph of f of x equal to 2x cubed minus 6x squared plus 1. So with polynomial functions, you will not have any restrictions on the domain. So your domain is all real numbers. Also, polynomial functions do not have asymptotes. So no asymptotes for us to worry about. Okay, the y-intercept is easy to find. Y-intercept is when x is equal to 0. Since 0 is in the domain, if you plug in 0 into the original function, you get that your y is 1. So whenever you're looking for actual points to graph, you always go back to the original function. All right, so now our derivatives. So we find f prime, you get 6x squared minus 12x equals 0. We factor that, 6x times x minus 2, you get two solutions, 0 and 2. 0 and 2 are my critical points. My critical points are potential max or min values. So we do our first derivative test here to determine that. Put 0 and 2 on the number line, put them in order. We take a test point less than 0, plug it into f prime. This is the easiest place to determine the sign. So if I pick negative 1, you'll get a product of two negatives, which is positive, means the graph is increasing. Then pick something between 0 and 2, such as 1. You get a positive and a negative product, so it's a negative result, that's decreasing. Pick something greater than 2, like 3, it's positive again, it's increasing. So to summarize the behavior, it's increasing from negative infinity to 0 and from 2 to infinity and decreasing from 0 to 2. Okay, but our first derivative test allowed us to figure out that we also have maxes and mins. So we have a maximum at 0, and when x is 0, your f of 0 is 1. So I have a max here. And I have a minimum at 2, again, because it goes from negative to positive. The first derivative goes from negative to positive. And when x is 2, f of 2 is negative 7. Don't forget that 0, 1, and 2, negative 7 came from substituting back into the original function. Okay. Let's move on. We're going to look for a second derivative. So if your first derivative was here, 6x squared minus 12x, your second derivative becomes 12x minus 12. So we set that equal to 0, and you get x is equal to 1. That means that 1 is a potential inflection point. So because I only found one answer, you only put 1 on the number line. And we test it, right? We're going to test if this is an inflection point, and we're going to test it by plugging into the second derivative, which is right here. Pick something less than 1. 0 is an easy choice. You get a negative result, means it's concave down. Pick something greater than 1, like 2. Plug it in, you get a positive result. That means that the graph is concave down from negative infinity to 1 and concave up from 1 to infinity. And the test told us that 1 is an inflection point because it changes signs from negative to positive. The second derivative changes signs from negative to positive. So 1, f of 1 is an inflection point. And if you plug in 1 into the original function, you get that your y value is negative 3. All right, so we need to put all of that together, and that's here on the right. This is the graph of y equals 2x cubed minus 6x squared plus 1. So we plot our maximum and minimums. Remember, I had a max here at 0, 1, and a min here at 2, negative 7. That's the points indicated in green. And I had an inflection point at 1, negative 3, so that's here, and I put that one in black. So inflection is where the graph changes from concave down to up. So let's make sure that our intervals of increasing, decreasing, and concavity work. So you can see here, it's increasing from negative infinity to 0. That's true, increasing. And it's also increasing from 2 to infinity, also true. And it's decreasing from 0 to 2. Remember, these are these intervals here, the ones here for increasing and decreasing, those are intervals of x, not y. Those are intervals of x. So from 0 to 2, it is decreasing. Also true. Okay, so we're in good shape for increasing and decreasing. Let's make sure our concavity works. So it is concave down from negative infinity to 1. So that's what you see right here. It's concave down from negative infinity to 1, but then it's concave up from 1 to infinity. So everything matches up with what we expected. That's, again, a pretty accurate graph. All right. So here's one more, another rational equation with a little bit more to keep track of than our first example. We want to sketch the curve of y equals 3 over x squared minus 1. So this one also has restrictions to the domain. I'm just going to change my color so it's different than the color that you see here. I'll make it this color. So in order to find the restriction on the domain, we take the denominator, set it equal to 0, and here you get two solutions. So here x is equal to plus or minus 1 when you take the square root, which means I have two restrictions on domain. So that's indicated right here. Your domain is from negative infinity to negative 1, and then from negative 1 to 1 and 1 to infinity. All open intervals do not include negative 1 and 1. Y-intercept is easy to compute. Plug in 0 for x. 0 is in the domain, so that's okay. And you get 0, negative 3. So again, everything in the green box is going to be something that you want to show on the graph. Because I had restrictions on the domain, I'm going to have vertical asymptotes at negative 1 and 1. So vertical lines are indicated as x equals, so that's why I have here x is equal to negative 1 and x is equal to 1. And I have a horizontal asymptote as well. If you take the limit as x approaches infinity of 3 over x squared minus 1, well, the numerator is always constant. So as my denominator gets larger and larger, 3 over a really big number or 3 over infinity is a very small number, so it goes to 0. So y equal to 0 is my horizontal asymptote. All right, so derivative. I took our original equation, which remember is right here, 3 over x squared minus 1, and I rewrote it as you see here below, as y equals 3 times x squared minus 1 to the negative 1. And that's again to avoid quotient rule. Quotient rule takes a little longer than chain rule, but if you choose to use quotient rule, you should get the same answer. So when I use quotient rule, do power rule on the outside based on this. So that's negative 3 x squared minus 1 to the negative 2, and then take the derivative of the inside, which is 2x, and so you see that right here. Right, so in the next line, you simplify. So I get negative 6x over x squared minus 1 to the second power. So I also rewrote the negative exponent, put it below. That's the equation that you set equal to 0. So unlike my other rational equation, this one actually does have a solution because you can solve the numerator for 0. It's not a constant. It has a variable term on top. So I have negative 6x equals 0. When you solve it, you get x is equal to 0. That means that 0 is a critical point as well as the restrictions on the domain. So here I have my restrictions, negative 1 and 1, as well as 0 on my number line. The only one that could potentially be a max or a min is 0 because 0 is in the domain, negative 1 and 1 are not. All right, so now we test it by picking test points in between each of these numbers. So you're going to have to test 4 times. And when you test, you always plug in to the derivative. So this is your first derivative test. All right, so if I pick something less than negative 1, like negative 2, and plug it in to my first derivative, you get a positive result. That means it's increasing. If you pick something between -1 and 0, like -0.5, well, it's still positive, so it's still increasing. But remember, there's an asymptote at -1. Pick something between 0 and 1, like a half, you get a negative result, so it's decreasing. And pick something greater than 1 and plug it in, and it's also decreasing. And same thing, you're going to have an asymptote at 1. So in summary, your graph is increasing from -infinity to -1, and again from -1 to 0, and it's decreasing from 0 to 1, and again from 1 to infinity. But that means that I have a maximum point at 0. And when x is 0, your f of 0 is -3. Remember, we found that point earlier. It also happens to be our y-intercept. So 0, -3 is your y-intercept. It's also your maximum point. Okay. Second derivative. Second derivative is based off of our first derivative. First derivative is right here. This time, I wouldn't try to avoid quotient rule. Just use quotient rule because you have a variable expression in both the numerator and the denominator. The work for quotient rule is here on the right. So my f from my y prime is going to be -6x. F prime is -6. My g is the denominator, x squared minus 1 to the second power. And g prime, you have to use chain rule. It's 2 times x squared minus 1 times 2x. Simplify it, you get g prime is 4x times x squared minus 1. So now all that work gets plugged into your quotient rule, which you see here. So that's g f prime minus f g prime over g squared. So in the next line of your second derivative, I factored out an x squared minus 1 because that's the binomial expression that they have in common. And when you factor that out of the first product, which is right here, you're left with -6 times x squared minus 1. And so that's what you see here. I distributed it. -6x squared plus 6. And when I factored out the x squared minus 1 from the second product, which is over here, you were just left with this -6x times 4x. Well, that's where the 24x squared comes from. Okay, so factor that out, and then you want to combine like terms inside of the bracket and also cancel the x squared minus 1. So this one here will cancel with 1 from here. So in the next line, you see that I have x squared minus 1 to the third instead of to the fourth because it canceled. And inside the bracket, that's simplified to the numerator, which is 18x squared plus 6. Again, that's an equation that you set equal to 0. And so with rationals, that means just solve the numerator for 0. So I'm here. So I have 18x squared plus 6 equals 0. I'm going to try to use square root method. So subtract 6, divide by 18, and you're left with x squared equals -6 over 18. Remember, -6 over 18 is the same as -1/3. So when you take the square root of both sides, you actually end up with an imaginary number. An imaginary number cannot be graphed on an xy plane. So what that means is that because you didn't get a real number solution, that means there is no inflection point. Okay, no solution means no inflection point. Okay, but that's okay. You can still find concavity. And so when I check for concavity, which I'm going to do right here, you still have to keep track of the restriction on the domain, which are -1 and 1. So if I pick something less than -1 and plug it into your second derivative, which is here, you will get a positive result. If you pick something between -1 and 1 and plug it into your second derivative, you'll get a negative result. And if you pick something greater than 1, you'll get a positive result again. So to summarize concavity, it is concave up from -infinity to -1, and again from 1 to infinity, concave down from -1 to 1. So even though there's a change in sign from positive to negative and then from negative to positive, -1 and 1 are not inflection points because they are not in the domain. So that's important for you to remember. All right, so all of this information has to be put together into a graph. And so that's what you see here. So first, let's make sure we put our asymptotes there. Remember, I had asymptotes at x equal to -1 and 1. So those are the vertical green lines that you see. And there's a horizontal one at y equal to 0. Y equal to 0 is your x-axis. So I tried to show it here as best I could. So that helps to guide where your graph belongs. Remember, we only had one point, our maximum, which is also our y-intercept, at 0, -3. So that's the point here in green. All right, so now we have to really use all of this other information to get an accurate picture. So we know that the graph is increasing. So now I'm looking here in this box. It's increasing from -infinity to -1 and from -1 to 0. So this is increasing. This is increasing. So far, so good. It's decreasing from 0 to 1 and from 1 to infinity. From 0 to 1, it's decreasing, and it's decreasing from 1 to infinity. Okay, so our increasing and decreasing portions look good. Oops, I erased the wrong thing. Let me put my graph back on there. Okay, now let's talk about concavity. Remember, it's concave up from -infinity to -1 and from 1 to infinity. So that's what you see here, concave up from -infinity to -1, concave up from 1 to infinity. Okay, so if it's facing upward, that's considered to be concave up. And it's concave down in between. In between -1 and 1, it is concave down. So that's the portion that you see here below that looks like an upside down parabola. So everything matches up with what we found, and that is again a pretty accurate sketch of the curve. So now you should try doing the homework for this section. Hope this helped.